Hi Algebra 2 students. This is the video for section 6.4, which you want to watch after finishing your quiz in class today. So we're going to continue on in chapter 6, and the next piece that we're covering is from section 6.4 and is going to go over what it means for something to be an inverse function. So if you want to have your textbook out while you go along with these notes and this video, that might be useful as well, just to see a few additional examples and a few more formal explanations in some parts. So the idea behind an inverse function, we're just going to go ahead and get started right away with a definition. So an inverse function is one that changes the input and output relationship of the original function. Input, output. And so what that means is you're essentially going to swap your x and y values. So if you have one function and you plug in the number 2 as your x input and get out y as your 4 output, an inverse function is just going to flip-flop that relationship. So instead of going from a 2 to a 4, you would go from a 4 to a 2. So I like to think of it as a function that undoes, or is kind of the undo button for an original function. So it's really just going to flip-flop that input and output relationship. But it's also useful because anytime we do something in math, we want to know how to undo that same operation. If you square something, we need to be able to take square roots. If we cube something, we need to be able to take cubic roots. When we multiply, we need to be able to divide. So it's that sense of opposition that comes along with inverse functions. So we're going to start off by finding the inverse function or the inverse equation for a linear function for a line. So this will be a pretty straightforward example. We're going to start off with this y is equal to 5x plus 1. So the first step to solve for an inverse function is actually kind of a fun one, I think. All that you're going to do is flip your x and y values. So anywhere the x's are, you're going to replace them with y's and vice versa. So instead of saying y is equal to 5x plus 1, I'm going to say x is equal to 5y plus 1. And then that's actually already my inverse function, but what I want to do is get y by itself, so it reads the same way my original function does. So to get y by itself, I'll subtract over 1. So I'll have 5y is equal to x minus 1, and then I'm going to divide both sides by 5. So I'll have x over 5 minus 1 over 5 is equal to y. And then just because I like to have y on the left-hand side, I'm going to say y is equal to x over 5 minus 1 over 5. So this is my inverse function. So y equals 5x plus 1, that was the original function that we were working with. Our inverse is this function here. So it asks, identify the relationship between the input and output values of the original function and its inverse. So let me show you what I mean by that. It doesn't matter which number we would pick to originally plug in, but if we plug in some x value to our original function, we're going to get out a corresponding y value. If we take that y value and go to our inverse function, we're going to end up with the original x value that we started with. So let's just pick an easy number to operate with. Let's try picking, let's just do 1. So let's evaluate this at x equals 1. So that's going to give us y is equal to 5 times 1 plus 1. 5 times 1 is 5 plus 1 is 6. So our y value is 6. So the way I can check that my function is its inverse is if I plug 6 in down here, it's going to get me back to where I started at x equals 1. So let's try that. So at x equals 6 here, because I'm flip-flopping, I'll end up with y equals 6 over 5 minus 1 over 5. Those fractions have the same denominator, so I'm going to get 5 over 5, which is 1. So my input and output are flipped here. So I had an input x of 1, output y of 6. So if I flip that, input x of 6, I get an output y of 1 when I have my inverse function. So that checks out here. I do want to compare how these functions look graphically because inverse functions are going to have a particular type of relationship that we can observe visually in addition to their algebraic relationship. So the first function we have is 5x plus 1. So if I want to graph that, that's just a line. So I can start by placing my y-intercept here and then going up on my slope. So 1, 2, 3, 4, 5, and over 1. So if I grab my ruler to make a straight line here, this is going to be my first function. This is going to be the original y. And then if I go to graph my inverse function, let's do that in green here. My y-intercept is negative 1/5, so kind of maybe right about here. And then my slope is 1/5. That x over 5 is the same thing as saying 1/5 x. So I'm going to go up 1 and over 1, 2, 3, 4, 5. And then I'm going to sketch a line between those 2 points as well. If I can get my ruler to cooperate here. Now, if I want to label this function, the way that we can label inverses is like this. We say y, and then we have a superscript of -1. So that's not the same thing as a -1 power in math notation. That specifically, that superscript notation means inverse. So the way that these two functions are related visually, what I also want you to draw on your graph is just the line y equals x, which is a line directly through the origin. So let me kind of try to get my line graphed here. So this line is the y equals x line. So inverse functions are related to one another in that they are reflections of one another across this line. So if I started here and just go directly across this line, I'm going to end up right here at that original piece, or vice versa. So they're kind of like mirror images, but specifically across the line, that diagonal piece of y equals x. So there's one more formal piece of algebraic work that we want to know about how inverse functions relate to one another, and we're going to dive into that in this example number 2. So we're going to talk about a new set of inverse functions. So this example asks us to confirm that the following two functions are inverses of one another using a specific definition. So on page 438 in your textbook, you have the formal kind of key concept piece in the blue box of what inverse functions mean to one another. So we talked about function composition quite a lot in section 6.3. And one of the unique things about inverse functions is that if you take their composition one way, meaning that if I evaluate f of g of x, where f of g of x are functions and they're inverses of one another, I'll end up with just an x. And then if I flip-flop that operation, if I take g of f of x, so I reverse the composition, I'll also end up with x. So that is a unique result that occurs both directions, and that's only ever going to happen for inverse functions. So if I take a look at the two functions that are provided, I could start out with either one and solve for the inverse using that flip-flop of x and y process we saw up above, or I can use this function composition technique. So let's try that technique out. First up, I want to evaluate f of g of x, which my g of x is x over 4 plus 3 over 4, so I can rewrite it like this. And what that means is anywhere I see an x here, I'm going to replace that x with this entire operation. So this is going to become 4 times x over 4 plus 3 over 4. And then I'm subtracting off 3 at the end here. So let's go ahead and distribute this 4 in. If I distribute the 4 here, my 4 top and bottom are going to cancel, and I'll just have an x. And then same thing here, the 4 here and this 4 down here are going to cancel, so I'll have x plus 3. So then I have this minus 3 on the end, this plus 3, this minus 3, they're going to go away, and I'm just going to be left with x. So that matches this result. I took the forward composition of f of g of x and I ended up with x. So then let's try it in reverse. Let's find g of f of x, which this time means I can replace f of x with its operation, which is 4x minus 3. And then wherever I see that operation in g of x, I'm going to replace the x with the entire 4x minus 3. So this is going to become 4x minus 3 over 4 plus 3 over 4. And these are fractions, but they're the same denominator, so I can actually just add my terms directly across my numerator. So this 4x, can't combine it with anything, but this minus 3 and this plus 3, those values are going to go away, and I'll just have 4x over 4. My 4's will cancel, and I'll be left with x. So that matches up here as well. So those functions are inverses of one another, And again, I could have found that out using the flipping of the x and the y and then solving to get y by itself, and I would have gotten that same result, but I can also check it this way too. So let's go ahead and extend that work from just linear functions to functions that have an exponent. So what we've been talking about most recently, so things like x cubed, x to the fifth, those kinds of functions we'll see a lot with inverses. So first up in example number 3, I'm asked to find the equation of the inverse function for the function that I have here. So what we have is x cubed. So when you have the notation of f of x and you're going to try to find the inverse function, go ahead and replace that f of x with y, just because it's going to be a little bit easier to work with algebraically as far as what we're used to. Then we need to swap our variables. So we're going to swap x and y here, which means I'm going to have x is equal to y cubed, and then I need to get y by itself. So in order to do that, I'm going to take the cubic root of both sides, and taking the cubic root of y cubed will just leave me with y. So I'll have y is equal to the cubic root of x. Now, at that point, I do just want to put it back into function notation. So since I wrote it like f of x, I would want to, so I'm going to just flip-flop this so it's on the same side as what we're used to. Y is equal to the cubic root of x. I'm going to put this into f of x notation as well. And then because I specifically want to identify that this is the inverse, one thing that I'll do is just include a little -1 superscript there. I apologize, that's kind of small, so let me see if I can make that a little bit clearer. Down here I'll have f, and then that -1 superscript indicates that I found the inverse. So my original function, f of x equals x cubed. My inverse function is the cubic root of x. So it's pretty easy there to see how the inverse relationship is going to undo the original function, because whatever I plug into something cubed as a value, if I plug that into a cubic root, I'm then just going to reverse that. So that's this next step, and that should be pretty easy to see here. So identify the relationship between input and output values. Let's just pick a value to plug into the original function, y equals x cubed. So let's, for instance, plug in x equals 2. If I do that, 2 cubed, my y value would be 8. So then if I go to my inverse function over here, where I have y, or the inverse of f of x, is equal to the cubic root of 8, I'm going to get 2. So whatever I plug in for 1x and get out that y, if I take that y and plug it into the inverse function, I'll get back to my original x. Now we want to to compare the two functions graphically. So my first function is x cubed. And what I would recommend is just picking a few points to plug in and get the y values out. So for instance, let's plug in -2, -1, 0, 1, and 2 for x cubed. So if we plug -2 in as our first point, we're going to be down at -8. -1 is going to be -1, 0, 1 and 1, 2 and 8. And so this function we graphed quite a lot back in our polynomial unit. This is just our cubic function. So this is what we would call f of x. Now our cubic root function is one that we haven't spent a lot of time graphing in class yet, but we are going to be graphing it together tomorrow. You can also graph that on your graphing calculator, or we can just pick some values to plug in. So let's go ahead and plug in -8, -1, 0, 1, and 8 into the cubic root of x. So if we plug -8 into the cubic root, that's going to give us -2. So we're going to be right over here. -1 would also give us -1. 0 would give us 0. 1 is going to give us 1. And then 8 is going to give us 2. So the cubic root function is going to be kind of this sideways snake function. So it looks like this. And I'm going to label this f with the superscript of -1 to label that it's the inverse. So just like before, if I go to superimpose that y equals x line, so if I'm right about here, this is my y equals x, I can see that I have that mirror image relationship again across this line. So I have that mirror image relationship again across this line. So this function, if I just go directly across this line, I end up exactly at this function here. So I'm going to go ahead and pause the video here because it will cut me off at 15 minutes, and then I'll fill in the last two examples for you on the next video.